Imagine that we built a huge staircase hundreds of kilometers long, so long that it would allow us to reach space. Let's climb it. You'd get a bit tired, but you could get high up. Really high, in fact. Much higher than Mount Everest. There's the idea that your death would be gradual, but in reality there's a sudden barrier, precise to the millimeter. A specific place high up in the atmosphere where suddenly you go to heaven. Metaphorically speaking, because literally you're already in the sky. But what is that barrier and where is it? To answer this question, we need to go to Nemo, but not the movie, the point. Point Nemo, also known as the Pacific Pole of Inaccessibility. The place in all the oceans that is farthest from any land, and by extension, for most of the time, the most remote place on Earth. The spot farthest from any human being. It is so remote that if we removed the water, we would see the seabed like this. A kind of post-apocalyptic landscape filled with the remains of spacecraft. This is because when a satellite or space station reaches the end of its useful life, it can no longer stay in orbit. So instead of letting it fall on a populated city, the last grams of fuel are used to make it fall at Point Nemo. Since there aren't even any ships there, there's no risk. At most, it might give a scare to a dolphin or two. Every few days, Point Nemo stops being the most remote place on the planet because it gets a visitor. Not from a ship, not from a submarine, not even from a plane. In fact, almost no route passes through the area, but from the International Space Station itself, with its astronauts on board. You might say, but they're in space. And that's true, they are. But here's the incredible part. Space is much closer than we usually imagine. The space station orbits just 400 kilometers above the Earth's surface. If you live in Barcelona, Spain or Guadalajara, Mexico, you're farther from your country's capital than you are from the space station when it passes overhead. The thing about the space station is that it flies much higher than it actually needs to. I say need to because the problem is that even if you're in space, there's still some atmosphere that slows down the spacecraft, making them fall. 400 kilometers high is a lot, and the record for the lowest orbiting satellite around Earth is held by the Japanese Tsubame at 167 kilometers.
67 kilómetros de altura.
And the thing is, the space frontier, unlike the one we explored in this video, is kind of blurry. Where do we draw the line? Well, maybe where the air ends, one might think. The problem is that it never really ends, it just gets less dense as you go higher. But it never actually reaches zero. If you ever released a helium balloon as a kid, there's a small chance that the atoms from the gas you let go into the atmosphere are now on Jupiter. And they're still technically part of the atmosphere. The internationally accepted boundary of space, more or less, there are some discrepancies, is the Kármán line. Nothing really happens there. It was set at 100 kilometers because it was an easy number to observe. It's roughly the altitude where, to avoid falling, it's more efficient to orbit than to fly, and where satellites that cross it can no longer complete even one more orbit without crashing due to atmospheric friction, more or less. If you manage to reach the Kármán line, we could officially say that you've reached space. If you manage to. Because there's one little problem to solve first. Survival depends on the available oxygen. The horizontal axis shows Earth's fixed atmospheric oxygen concentration, while the vertical axis displays atmospheric pressure and corresponding altitude. They scale together since the higher you go, the lower the pressure. It starts at the top at sea level and goes down until the pressure is almost non-existent. This is the safe zone, where there is enough oxygen to breathe normally. Since we can't modify the concentration of oxygen, which is 21%, we can only play with this vertical axis. That is, by varying the atmospheric pressure with altitude. That's why, if we go to places like the Dead Sea, where the pressure is higher than at sea level, let's remember that in that part of the Earth, the altitude is negative, meaning it's below sea level without being flooded. In this case, we are, surprisingly, in an area closer to the center of the safe zone, more convenient and efficient for our survival. If we do the opposite and lower the pressure without increasing the concentration, we enter the hypoxia zone, where your body starts to experience symptoms of lack of oxygen, confusion, dizziness, euphoria. But up to this line, the body can more or less acclimate over time by producing more red blood cells. This is why, if you take a person who lives at sea level and bring him to La Rinconada, Peru, the highest city in the world at 5,100 meters above sea level, he will experience severe symptoms of hypoxia. He will feel terrible while the locals will be more or less fine. The body's limit, which on Earth corresponds to the intersection between this line and the line representing the planet's oxygen concentration, is around 8 kilometers. The infamous death zone where no human can survive without supplemental oxygen, except for very exceptional cases of people who have managed to reach Everest without using it, thanks to extreme acclimatization and genetics, as well as fast ascent and descent times and quick rests that allow the body to rely on its reserves. Continuing with our space ladder fantasy, it would be as simple as setting up a souvenir shop at 8,000 meters, offering supplemental oxygen packages for those who want to keep climbing, with a complimentary photo. Once we've crossed this frontier, you might think that the Kármán line would be our next goal. But that's not the case, because before that, we would encounter the invisible wall that protects us from death. And the best way to enter is to travel to our neighboring planet, Mars. The red planet had a lot of water in the past, and much of that water didn't go anywhere. Where is it? Well, at the poles. Frozen, underground. Also frozen, and a small part in liquid form and as water vapor. But liquid water on the surface of Mars can no longer exist. Except at this point, Gelas Planitia, the key to our mystery. But why? The thing is, liquid water needs two things to exist. The right temperature and pressure. If you heat a pot of water on top of Mount Everest, you'll see it boils at 71 degrees, not at 100. If you keep going higher, you'll reach a point where it boils at 0 degrees. Since the freezing temperature is always fixed at 0 degrees at that point where freezing and boiling meet, liquid water simply can't exist. This is because the molecules in the liquid phase move so much that they need a really dense gas to suppress their attempts to escape. It's as if the liquid were a prison, and the air were the guards. If there are a lot of guards, no water molecule escapes. This is what happens at sea level. If there are fewer guards, they won't be able to contain the prisoners when the environment gets hotter, with riots like water boiling at 90 degrees on Everest. But they will be able to contain them when the molecules are calm and cold. But if even more guards leave, no matter the prisoner's temperature, they'll all escape. This is the case on Mars. In Gelas Planitia, you find the deepest point of the red planet at 7,152 meters deep. If you're curious how Mars depth is measured without oceans, we'll cover that in another video since it's complex. The fact is that in that area, the pressure reaches 1,240 pascals, which is above what's needed for liquid water to exist. It only happens in that small area of Mars. It really seems like a whim of the universe. And even though we don't have observations to confirm it, we suspect that in that corner, sometimes water flows just like it used to all over the planet. A small reminder of what was once a world full of oceans, rivers, and seas. 611 pascals is the pressure where liquid water can no longer exist. On Earth, this happens at an altitude of about 34 kilometers. And do you know what's made of water? Your blood. This would be the real limit if it weren't for the fact that at this point water boils at 0 degrees. But your blood is warm, so it boils sooner, at a much lower altitude. Remember that on Everest it already boils at 71 degrees. The so-called Armstrong limit is that invisible wall. At an altitude of 18 kilometers, human blood, which is mainly composed of water, begins to boil spontaneously due to the lack of atmospheric pressure. Death occurs in just over a minute if the pressure is not restored. Because of this, in order to keep climbing our imaginary ladder, we would need a pressurized suit like the ones astronauts use for extravehicular activities. But at this point, we would be more like a spaceship than a hiker. And that's what Earth is. A spaceship that, even though we don't see it, protects us every day from the deadly vacuum of space. Thank you very much for watching the video, and goodbye.